Hey folks, and welcome to the 6th webinar in the TOSCA Implementer Series. Our webinar today is titled Holistic Modeling of HPC, FaaS, and Edge Applications with RADON and SODALITE TOSCA Extensions. That's a mouthful. We have 4 speakers with us today representing 2 different organizations. This is truly a story of collaboration. I'll just share a few details before we get started today about our 4 guest speakers. The first one, Giuliano Casale, joined the Department of Computing at Imperial College London in 2010, where he is currently a reader. He teaches and does research in performance engineering and cloud computing, topics on which he's published more than 100 refereed papers. Domenico Presenza is senior researcher at the Engineering R&D Lab. Currently, he is leading the team developing SARA, a socially assistive robotic solutions envisioned for the engineering's area's healthcare suite. Dragan Radolovic's background includes work in the financial field, banks, financial institutions, and other software industry as a software architect and project manager. His main points of interest are cloud architectures. Currently, he works at X Labs Research as a project manager and is the work package leader for the SODALITE H2020 project. Kamil Tokmakov joined the HPC Center in Stuttgart as a research engineer. He is currently working in the SODALITE project and responsible for modeling and orchestration of HPC use cases. His current research interests are cloud and HPC infrastructure, SDN, and network coding. So as you can see, we have an illustrious group with us today. We will have closing comments by Chris Lowers. Chris is the CEO of Ubicity, and he is the chair of the OASIS TOSCA Technical Committee. As you can see, the meeting is being recorded. We will follow up with the link after we finish up today. We will be taking questions at the end, so feel free to post your questions in the Q&A bubble below, as you can see on your screen, and we will get to those when we can. And with that, and sorry for the butchering, I took a pass at it. So thank you so much for your patience, and we'll start with Giuliano. Thank you.
Thank you very much, Dee. Let me share the screen, and you should see my slides now coming up. So thank you very much for the kind introduction, and thank you to OASIS and the TOSCA TC in the first place for inviting us here today to speak. The story that we want to tell is a story of a collaboration between 2 projects, 2 research projects, RADON and SODALITE, that have worked together to develop a number of extensions to TOSCA that can be applied to holistically model HPC, functions as a service, and edge-based applications. These 2 are research projects funded by the European Commission. They comprise respectively 8 and 9 organizations, and we focus on the RADON side on applying TOSCA to the design of serverless-based applications, and in particular, we are developing an advanced DevOps framework with IDE based on TOSCA and its extensions. Whereas SODALITE has focused their work on high-performance computing and cloud, and so they're using TOSCA to deploy and manage applications on these targets, and also have built an environment comprising several tools and a smart IDE to model using TOSCA these kind of applications. And we have established among these 2 projects a collaboration this year that has led us to study the problem of how we can use TOSCA to support the deployment and the operation of applications that span across as we said, HPC, cloud, edge. And clearly, there are several architectural approaches to design these applications. So modeling can help in reasoning on these architectures. But when you look at the different tools and software engineering frameworks that are out there, they tend to be specific either to just a subset of these deployment targets, or maybe they are specific to a particular platform like Azure or AWS, and therefore we found quite difficult to find a solution that was really holistic and allowed modeling and also the development of tools on top of these models to design and operate hybrid heterogeneous architectures. And when we looked at what TOSCA can do for these, of course, there is a lot out there, but there were also a number of limitations. So for example, if you think to function as a service, there is event-driven behavior, like events that trigger the execution of functions. So how do you express this in TOSCA? And often functions process data in flight. And so how do you make this data in the underpinning streams a primary citizen in the TOSCA model? And on top of this, how you use these extensions to build frameworks that really leverage these extensions. And our proposal that we jointly developed among the two projects is this new hybrid compute profile is released at the GitHub repo you see in this slide, and is a proposal that we have defined in collaboration also with the TOSCA Emerging Compute ad hoc committee. We would like to illustrate the work we have carried out concretely, looking at two use cases. One comes from SODALITE and looks at water availability prediction, focusing on computation of snow-related indexes that predict the availability of water. And the other comes from RADON and focuses on assisted living, and so how edge devices can be used to assist, for example, the elderly, think to situations like fall management. In this first part of the presentation, we will look at the SODALITE Snow use case, and I will spend a few words to introduce it before handing over to my colleagues. This use case has been defined by Politecnico di Milano, which is a university based in northern Italy, quite close to the Alps. And so as part of their collaborations, they are trying to come up with a system that can analyze publicly available images of the Alps and there's no situation on these mountains to predict water availability. And this is, of course, because in mountain regions, water is often stored as snow on the mountains. And in order to build a system that does this automatically, you need to have a fairly complicated data pipeline that is able to pull content in terms of images coming, for example, from users, think to social media or sources on the web, but also possibly webcam images that are pointed to particular mountains that collect periodically images. And so this kind of information is naturally quite heterogeneous, and you tend to need a set of operations that form together a pipeline to be able to come up with a computation of indexes related to the snow that provide this information about water availability. To give you a better sense of this kind of use case, what you might have is this set of several images. I'm showing here 11 images that show the same mountain from different angles in different types of illuminations. So the weather condition can be also different. And so you need all these filters to come up with a, say, daily median image that gives a sense of the status of the snow on the mountain for the day. In terms of the challenge when we look at TOSCA deployment and management, let's try to see how we can implement a system like this. And this is an architecture that gives an example of hybrid deployment across HPC, cloud, and involving also edge and function as a service. So in this system, we have a part of the architecture that deals with offline training. And so these images we have been seeing can form a training data set. In our installation, this is hosted on S3 on the cloud, and therefore needs to be transferred to an HPC facility where the complex scientific calculations related to these snow indexes, as well as the filters, can be considered at this stage to build a neural network model that is able to make predictions about the water availability. And this model is moved then to other services in the cloud that process the largest amount of images. So you use the trained model now to test the neural network on the images over time. And this information, together with the images themselves and the indexes, is then moved towards a front end, say regional snow news front end, where a number of pre-filtering steps through function as a service functions are applied, for example, to create thumbnails that are exposed on this front end. And this front end can also receive contributions from edge devices like community images taken by smartphones that can be processed also potentially at the edge. Think, for example, to scientific units that take images of certain mountains from a base camp. They can have their edge devices that then update these images on the front end. And moreover, these images can be fed back to the HPC space for further training. So the problem we are trying to address is how we can orchestrate something so heterogeneous and complex using TOSCA. And so I hand over now to Camille for seeing how we did this. Thank you.
Thank you, Giuliano. Right. So I will provide the highlight of the hybrid computing profile and its TOSCA node types for HPC, cloud, and FaaS, and to show how we connect the application components deployed over these various heterogeneous platforms. And at the end, I will show the 2 demos of the work we've done so far. So there exist platforms that we could take advantage of when we want to decrease the execution time of hybrid applications. So for example, one could utilize HPC resources to execute batch computation in a performant way, such as machine learning training or scientific simulations. In cloud, we usually use and scale our own virtual infrastructure and host services. And using serverless and FaaS platform, we can perform certain computation, also called functions, in a very scalable and distributed way without the specification of certain infrastructure. So the hybrid compute profile we're developing exactly for this reason and allow users to deploy their hybrid application components onto these platforms and connect the components into the workflow or pipelines. So the profile itself basically is a set of TOSCA libraries and Ansible playbooks that allow us to do that. And we are currently supporting deployment of batch components into HPC managed by Slurm or PBS workload managers. For cloud, we are provisioning resources and deployment over OpenStack and AWS. And for the serverless, it is OpenFaaS, AWS, Lambda, Azure, and Google Cloud Functions. So for the HPC, we develop node types that define types of clusters. Either they're managed by the workload manager or simply a set of compute nodes where application can be executed at. And if an application is containerized, we also provide support for Singularity runtime, which is used mostly in HPC due to the performance and security, and also the definition of application parameters. For example, what is the executable arguments, how many MPI ranks if the application is parallelizable. And the application can be encapsulated into the batch shop, where we define the job parameters, like wall time, number of nodes, whether we want to some specific nodes like GPU nodes, and the multiple jobs then could be put into the workflow and would be executed in the specific order, and independent jobs can be even parallelized. For the cloud, we develop node types for provisioning of certain resources, virtual machines, security groups, key pairs in AWS and OpenStack, and also the creation of Docker environment like host network, certificates, volumes, and the application components, basically in the form of containers. An example of a cloud deployment shown in the figure below, where we have the OpenStack VM, which depends on the key pair and the security rule, and the Docker host and the registry and the network are hosted on this VM, and basically the Dockerized component is hosted on the Docker host, and also the Docker volume. And the Docker component is basically depends on the Docker volume. With respect to the serverless and FaaS, we have TOSCA node types for the specific platforms. As I said, it's Lambda, Azure, Google Cloud Function, OpenFaaS. These functions are triggered by certain events, such as storage updates and API requests. And for the notification and function triggering, we developed an invoker requirement shared between the entities that produce events, such as API gateways, object storage, and another function that's shown in this picture. And the specific platform should implement its own mechanism to trigger a function via events. So for AWS, there is an Ansible module for S3 bucket notifications. So when an object is added into the S3 bucket, then AWS Lambda function is triggered. And as an example, we could see that there is AWS bucket and the function deployed in the node templates, and the S3 bucket, which is the object storage, has the invoker requirement with the relation to the function, and it has also the relationship template AWS triggers, which is triggered on this certain event when the object is created. So far, I explained the node types that we could deploy and the component of the components into the particular platform. However, there are often the cases when we would need to transfer data from one platform to another, for example, from HPC to cloud or from cloud to FaaS. So while in cloud and FaaS world, there are quite a lot of methods for data transfer, where HTTP, FTP, or S3. In HPC, the connectivity is limited due to security constraints, and only SSH and grid FTP are supported. The grid FTP is a special FTP, let's say, type that allows us to send securely and more in a more performant way using the multi-threads. and send the data in parallel. So to resolve this, basically the data management over hybrid platforms, we used Apache NiFi, which is a cross-system data flow service, which already supports the connectors to various cloud storage system and stream platforms. And we extended it to support the grid FTP connector. So with these connectors, for our cases, it is now possible to define a pipeline block that transfer data from one supported platform into another. So for example, now we could establish the connection between the cloud connectors and HPC. And approach we use that we model such pipeline blocks in TOSCA and orchestrate their lifecycle using NiFi REST API, which is basically exposed after the deployment of the NiFi. So what is the data pipeline block? So this is the entity which executes the pipeline tasks, such as data processing, API calls, invocation, fetching or pushing data to storage system or stream platforms. And internally, it has the ingestion and emission queues used for buffering of input and output data. And using these queues, multiple pipelines can be connected, forming a group. And the input and the output pipes are the gateways for receiving and forwarding data to the external data endpoints. So apart from pipeline blocks designed for data transmissions, for example, the source and the destination ones, we also have the midway pipeline blocks that allow us to do some actions like encryption, executing some commands, also like calling functions or other remote APIs. And there is also a standalone, which basically used to perform independent activities, such as the copying from one S3 to another, and basically without passing data directly through the NiFi. As an example, we could see that how the two pipeline blocks connected and perform data transfer from grid FTP server in HPC infrastructure into the S3 in cloud. And there is one pipeline block is publishing data to S3, and another one is consuming data from grid FTP. And the grid FTP consumer is then connected to the S3 publisher via the requirements connect to the pipeline, which is common among all the supported data pipelines blocks that I showed previously, as you could see in this TOSCA snippet. Yeah. So now I'm going to show the demos. The first demo would be about the performing AI training for one of these Snow use case components with the data set taken from the S3 bucket, and the resulting inference model would be moved to another S3 bucket. So this is the S3 bucket for the training dataset. And this is the S3 bucket for the inference model. So we firstly upload the dataset, which is currently a small one, just for the sake of the demo. Usually they are 100 of gigabytes. Oh, yeah, not 100, but yeah, quite larger than the megabytes. Yeah. So we now uploaded the dataset, and then we basically execute the service template designed for the training and getting the data from S3 and sending it to S3 via grid FTP. So now we're deploying the resources needed for NiFi instance. So NiFi is deployed on a VM. So for that, we need a key pair, security rules, and VM itself. And then we deploy the NiFi instance onto this VM. Now we create the NiFi pipeline block that publishes data to the GridFTP endpoint, and create the NiFi process that will consume the data from S3. And then we basically connect these two pipeline blocks. Yeah, but right now we check that there is a data set is absent at the moment. So now we connect these two data pipeline blocks, and this will move data from S3 to the GridFTP server via NiFi. And then we check. As we could see, the data set was moved. Now we're observing the execution of the training. You could see that it's running, and it is in the GPU queue. That means it uses the GPU nodes. And we see that the job now is completed, and the inference model is produced. Then this model will be moved to another S3. Again, we create the pipeline block to publish the data to S3, then create the block for consuming data from GridFTP, and then we connect them together using the connect to pipeline requirement. And we see that the deployment is complete. And then we check that now we have the inference model moved. So another demo would be about the generation of thumbnails of the resulting processed images of the mountains after the snow computation pipeline. And then these thumbnails would be then used by the weather report front end, and we soon plan to extend it with additional useful data like geoposition and the interpretation of the snow index to show warnings, like if the snow index is close to critical. So here we have the bucket for the processed images that would be at the end of execution of the pipeline. Then we have the bucket for the thumbnails. And then this is just the dashboard for AWS Lambda. So now we execute the service template. Again, we create the resources needed for the snow use case and its component, like the VMs, key pairs, the security rules. And then we deploy the snow use case components, which are Dockerized. So once it is completed, now we move to the part of creation of NiFi instance, which will then move data from the images that we generated in the snow use case, and then move it to the S3 bucket. So we're creating the NiFi process that will consume the data from the local file system and move it to the S3 bucket. In a similar way, we specify the connect to the pipeline to connect those two pipeline blocks. So once it's done, we create the Lambda functions and configure the S3 bucket for triggering the events, which I showed previously with the S3 object create event. So once it's done, we check the results. Now we see, so now we see that we have received the images, and then we see that the Lambda function was deployed, and then that it generated the thumbnails. And then we just comparing the results, checking how it looks like. So we take the daily meridian image, processed image, and then we just see how it looks like as a regional image. And how it looks like resized. Yeah. So with respect to the edge deployment, as an early prototype, we also developed the thumbnail generation at the private edge cluster using OpenFaaS and MinIO. There we have the lightweight Kubernetes cluster over the cluster of Raspberry Pis, and the image can be shared with neighboring Android devices, creating the thumbnails. So what we still require is the integration with the data pipelines managed by Minify. So basically the lightweight version of NiFi, so that we would respect the resources at the edge. And basically this is what we need to complete the end-to-end service deployment. So far we experimented with the AWS S3, Lambda, and GridFTP, and we would like to extend it to the open source technologies like OpenFaaS and MinIO, and we would like to also apply the development to another edge use case of SODALITE vehicle IoT, which is basically an automotive use case. So these are the current state, the limitations, and the future work. Now I will hand over to Dragan Radovic, and he will present the orchestration. Thank you.
Thank you, Kamil. I'll start sharing. Okay, hopefully you can see my screen now. As you saw before, it's fair to say that behind every good TOSCA project there is a specific engine called the TOSCA orchestrator, and in both projects we use the XOPERA TOSCA orchestrator developed by XLab. And then to put some context around this, we actually want to show some history about the development of the XOPERA TOSCA orchestrator. So we first met TOSCA in the DICE project, which was about modeling the big data pipelines, and we at this project we use the Cloudify and its own let's say TOSCA flavor and also developed some plugins for Cloudify, and we found this very painful for covering different platforms. And at the same time, we also started looking at Ansible, which was gaining popularity at the time. The Ansible, which is a configuration management tool and the deployment tool also, but it had its own shortcomings at that point with regards when the deployment gets large. You have to take care about the inventories, the large part of the inventories, the passing of the parameters is a problem, and things like this. So we thought, how about join these two technologies, the TOSCA that we met in DICE, and also Ansible for the execution of the life cycle, and so creation of the, let's say, a new orchestrator was the next logical step for us, because we were planning to expand on this topic on the cloud deployment, especially heterogeneous environments deployment for different applications. So we started working on the Xopera TOSCA orchestrator in 2018, and the first release was in May 2019, and the current release is 0.6.6 with the specific inputs from both of the projects, both RADON and SODALITE were actually supplying requirements to the Xopera orchestrator. So why Xopera was a fine fit for the two projects? First of all, the ease of the definition of topology abstraction in TOSCA is really great. And also we wanted to have maximum impact for the DevOps teams, because this was actually the target audience for us. We wanted to cover this deployment of the application over heterogeneous environments. And we really thought that Xopera would be a great fit for this part. So we chose obviously TOSCA because it's really easy to define and abstract the infrastructure definitions in nodes, and also application definition, and connect these two with the relationships. Of course, since TOSCA is an international standard, there is no vendor lock-in as in proprietary, let's say, implementations of various configuration tools. And also, most of the things that TOSCA is covering actually fit perfectly to both projects, such as the configuration of relationship between the nodes, and especially the application component nodes, and the policies, the triggers, and the workflows we want to define for let's say HPC defined job workflows. And Ansible is here because we implement the life cycle of the operation of nodes through Ansible playbooks. And we specifically chose Ansible because it's first choice among the tools for configuration management, for sure. It's really easy to learn. It fits perfectly with the TOSCA YAML because it's also, let's say, the definition of the TOSCA of Ansible playbooks is also very similar to TOSCA in its YAML, and it has a great community support and a vast selection of modules that can be reused very easily through these playbooks. And of course, the important point is that it is agentless by design, so you don't need to supply any agents to store or to execute on specific targets. Especially for HPC, this was a nice fit. So for Xopera, in a nutshell, what is the vision of Xopera? First of all, Xopera wants to be a very lightweight orchestrator, and we want to build an ecosystem that provides all the necessary tools for this kind of orchestration. And of course, the Opera orchestrator is one of those tools, for sure. It has its own state. It stores the state while it actually deploys the blueprints, the TOSCA Caesars. It supports TOSCA version 1.3. It was first CLI based, but now we have also a different implementation of the REST APIs. It can be easily encapsulated into Docker images. And also we have this Xopera SaaS variant, which can be deployed on premise and used as a software as a service. You see here the links, so it's really easy to start with Xopera and the examples there. Which are the main or the high-level features we wanted to support the use cases? First of all, the support for Resume Clean Start, which was one of the requirements for the HPC job workflow execution. This comes really handy when you have a large deployment or a large number of platforms to be deployed on, and actually when something breaks in deployment, you can actually resume the deployment from where it broke, or you can use the clean start option for starting all over the deployment. Also, we support the parallelization of the deployment within Xopera. This means that you can specify the number of threads that the deployment can use for instance, for deploying on different platforms simultaneously. There is initial support for Caesar diff and update, which means that you can actually patch the Caesar files, the Caesar blueprint, and deploy it over an existing deployment, and also see the differences between those blueprints. And of course, from the RADON perspective, a very important part was implemented with the implementation of policies through the notification and events of triggering of events, which we saw even before. Now I'll pass the word to the next use case, which is a RADON system living use case, Sarah, and I pass the word to Domenico.
Thank you, Dragan. I'm going to share the Dragan, maybe. Oh, okay. Dragan, please, you should stop sharing your screen. Otherwise, I cannot do on my side. Oh, Julian. Okay, thank you. Okay. So, as Dragan said, this use case is about a solution in the domain of ambient assisted living. In particular, Sarah, this is the name of the solution, is a system integrating home automation and a robotic system with the aim to prolong the autonomy and delay the institutionalization of elderly. Sarah provides health monitoring and assistance in daily living tasks to elderly and their caregiver while being at home. And Sarah is being developed by engineering as a prototypical module of the engineering areas solution in the domain of healthcare. Sorry. Oh, okay. So the Sarah provides to both, as I said, both to caregivers and elderly a collection of assistive tasks that can be broadly classified in four main classes. We have functionalities or assistive tasks, as I said in the Sarah jargon, to address physical decline and therapy. We have assistive tasks to deal with cognitive decline, health management, and to address the psychological needs of elderly. In this slide, you can see the main component and protocols used in the implementation of Sarah. And I want to draw your attention on the fact that the software components both are available both as a service in the cloud. This is the area Sarah part here in the slide, and other components instead are made available on field devices or wearable devices. So we can have a belt wear by the patients. We have the mobile phone of the patient, or we have traditional, more traditional home automation technology with the devices communicating via ZigBee. And we have also more advanced devices like a motorized and sensorized robotic rollator or a humanoid robot. We use a Pepper robot currently in our implementation. All these components, the communication between these field components occur via various protocols as indicated in this slide, and the field device and the services in the cloud communicate either via cellular network or landline or IP networking on the internet. In the context of the project, the objective of our use case was the re-engineering of SARA assistive task and Chloe IoT services to take advantage of the FaaS infrastructure. Just to clarify, Chloe IoT services are services offered by a platform that engineering use developed internally to address IoT specific requirements. So the IoT services comprise services to deal with management of devices, management of events generated by the field devices. And in the project, we focused on two assistive tasks from SARA, the full management assistive task and remote gate analysis assistive task. The objective was the re-engineering of these two assistive tasks to make use of the OpenFaaS platform. The choice for OpenFaaS platform is motivated by the fact that OpenFaaS can be also deployed on field devices, single board computers like the Raspberry we have on board of our robotic rollator. In this presentation, I'm going to focus mainly on the remote gate analysis assistive task. So in this slide, you can see that this assistive task indeed is a distributed application. We have a component deployed on board of the robotic rollator, and it is the gate sampler on the left side of the slide, and a gate server available as a service on the cloud. The overall objective of this assistive task is to create the gate sample representing the distance of the legs of the patient from the backside of the rollator, and cluster these time series in a way that general practitioner or specialist can use this information to assess the condition of the patient. On board of the rollator, the gate sampler take care of the actual sampling process, the sequencing of the time series and the encoding, and the transfer to the gate sample to the gate server, where the time series are clustered, encrypted, and stored for subsequent analysis. In this slide, I represent the way we re-engineered the solution in order to take advantage of the OpenFaaS and in general of the FaaS approach. On the field level, what we did is we factored out the stateless part of the gate sampler, and we encoded, sorry, the joke, but we took the encoding functionalities and made that available as a function on OpenFaaS. And on the cloud side, the whole gate server was decomposed in terms of its core functionality, and you can see here we identified the functionality to start a gate analysis session, stop a session, add sample coming from the sampler, proceed with the clustering, encrypt the cluster, and proceed with the storage. One of the advantage of providing the encoding functionality as a function outside the gate sampler is the fact that we envisage the possibility to deploy additional functionality on the rollator, so the functionalities of the rollator are not fixed, but we can add additional functionalities, and these additional functionalities, services for the patient, can take advantage of this encoding function and other function coming from other assistive tasks. So here we have a video that, by using the RADON graphical modeling tool, presents the function, the service template, accounting for the function present in this gate analysis assistive task. You see, on the left, you have the component residing on board of the robotic rollator with the encode time series functionality. And on the right side, the part residing on the cloud. You have the SARA cloud node with the instance OpenFaaS deployed as a service on the cloud, and the 4 main functionalities that we extracted from the previous gate server. Of course, these are not the only functionality that we have to implement the gate analysis task. Indeed, in this screenshot here, you can see all the components that we developed to implement this functionality. And in addition to the OpenFaaS instance you saw before and the functionality already presented, you can see that we also have a more traditional technology contributing to the realization of these functionalities. So we have the Java application that is gate sampler, we have a MongoDB time series database management system, and the like. And in here we have another short video presenting the Xopera orchestrator already introduced by Dragon Network. On the left side of the frame, you have you can see the GUI of the OpenFaaS instance deployed on board of the rollator that you can see in picture. And on the right side, instead, there is the OpenFaaS instance residing on the cloud. So here you should, if I may go, sorry, enable to. Okay, you see the video started. You see in the shell here the work being done by the Xopera orchestrator, and you see that the various functions start to appear to be deployed on the OpenFaaS instance that we mentioned. So you have the encode time series already deployed, and then you see the function to start, stop the session, add the samples added into the cloud. And to conclude this brief presentation, I want to mention just the benefit we observed during the realization of this use case. First, of course, we appreciated the reduction of cost introduced by the fact that we adopted the RADON TOSCA orchestrator. So in terms of this increased automation let now us to reduce the cost. In terms of technical implementation, of course, there is the benefit brought in by the adoption of the FaaS model. Now the management of the execution environment is no longer on the shoulder of the developer of SARA, but this is outsourced to the colleagues managing the open FaaS infrastructure. And also the benefit we appreciate is the reduced effort for the development of maintenance of the deployment bundles, and this thanks to the graphical modeling tool and the radon particles made available from the RADON project. And this slide concludes my presentation. I have here a slide that you can use to as an entry point to get more information about the both project, RADON and SODALITE. And that's it from my side. So if there are questions, I'm happy to try to answer.
So Chris, do you have a couple closing comments? We do have one question, but I thought we would take that after you make your comments.
No, I just want to comment about what an excellent presentation this was. It's a very comprehensive set of use cases that demonstrate the power of TOSCA, and use cases that are different from the sort of the early infrastructure as a cloud targets that were at the roots of TOSCA. So it shows the power of TOSCA and how it's evolved to really handle any type of cloud application, not just the original infrastructure as a cloud paradigm. And so I want to commend the presenters for excellent work and a very informative presentation. So thank you very much. I do want to leave a couple of minutes for questions. I think we have one or two in the Q&A box, so perhaps we can quickly go through those and then we can wrap it up.
We do. Okay, so first of all, an expression of appreciation for the valuable presentation that you guys made today, and thank you very much. I mean, that really was really, again, we're so grateful, and we'll do a good job at getting this out there and sharing it with other folks. So the question that we just have a couple of minutes. What were the design decisions in modeling using TOSCA? For example, why did you choose to model data pipelines using TOSCA? And again, thanks.
I think these, thank you for the very kind words and for this question. When you think to TOSCA modeling, with the data pipelines, you can have functions that react to events, and therefore you want to expose the data pipelines that carry the data that may be source of those events directly at the model level. Because if everything is hidden to the model, then it becomes difficult to annotate triggers for the function directly in the model. So that's an example of the reason why the data pipelines are explicit using TOSCA. But it is fair to say that there could be a more implicit approach where you don't see everything in the TOSCA model. It still works, but then you cannot predicate on what you don't see. And you see an example of this in the presentation we've just seen from Domenico with the SARA use case, because some of the functions there were declared implicitly, and so it is up to the user to choose the best approach. We support both.
Okay, so just again, expression of appreciation. Giuliano, Domenico, Dragan, and Camille, thank you so much. This was really valuable for us and certainly for all the folks that have joined us today. And with that, we hope everyone has a delightful afternoon.
Thank you very much for hosting us.
Okay.
Thank you.
Thank you.
Thank you very much.
Thank you for hosting.
You are welcome.
Goodbye.